Today I am going to discuss about the retro-pericyclic reactions. So here is the example of retro-Diels-Alder reaction. Now here there are two different types of groups, Z and the another Z, where the first Z, that is electron withdrawing group. So whenever a six-membered ring is there, and in the six-membered ring there has to be a double bond, and anti to that position there is a presence of substituent, and again that substituent is electron withdrawing. If this substituent is electron withdrawing, the presence of double bond in the six-membered ring and the anti-position of this there is a substituent, then we have to always go with the retro-Diels-Alder reaction. So the mechanism for this retro reaction, it gives the butadiene molecule and the substituted olefin. Now look at here, the first target molecule. Now the six-membered ring is there, double bond is there, anti to that this electron withdrawing group is there, double bond is there. So whatever the requirement is there for the Diels-Alder reaction, it fulfills over here. So go the retro reaction of this retro Diels-Alder reaction, write down here heating. The selection rule for this is pi 4s plus pi 2s. So supra cyclo addition reaction it is. So that you have to write down on the arrow. So the stereochemistry of this is whatever the stereochemistry in the reacted molecule, the stereochemistry retained in the final product that indicate it is a supra overlapping. Now due to the retro reaction, so after retro reaction, you can see the product is furan and a dinophile, that is dine plus dinophile. Now the synthesis, furan plus this is a dinophile. The combination of these two in heating, it gives the product. Now this is the new target molecule. Now in this target molecule, you can see here that this ring, and this ring. So look at this two ring, that this one is a six-membered ring. This is a six-membered ring, and in the six-membered ring, there is a double bond, and anti to that position, there is a substituent, and again, there is a presence of an electron withdrawing group. So the condition fulfills over here that we can go with the retro-Diels-Alder reaction for the ring. This is ring A, this is ring B, and this is ring C and D. So we can go the retro-Diels-Alder reaction for ring C and D. So again write down the heating here and complete the retro analysis. It gives this diene. So this is the diene plus dinophile. So look at the stereochemistry of HA and HB. As this is a cis double bond, so look at in the target molecule, the stereochemistry of HA and stereochemistry of HB is again a cis stereochemistry. So as the double bond is C, the stereochemistry maintained after the reaction, that is the stereochemistry is maintained in the final product. Now look at the C. This is again a after that A. Now look at this is a A compound which is a new target molecule. We have to consider this is a new target molecule and this one is readily available, that is a quinone. Now here, what are the things we can see? There is a one double bond which is outside the ring, and this double bond is just inside the ring. So which double bond we have to consider first of all? So for the consideration of this, look at here that FGI. So what is FGI? That this double bond we are going to consider, and we are doing the reaction of retro dehydration reaction. So retro dehydration reaction is what? You add the water molecule, but remember addition of water molecule, that is H and OH. These two things we have to add hydroxy group on more substituted bond. So this is more substituted bond. So always remember, add the hydroxy group on more substituted bond. After this, now this is what? This is a new target molecule, and this hydroxy group is a tertiary hydroxy group. So tertiary hydroxy group acts as a gliding functional group. So you disconnect this bond and remove this part. So it gives what? This compound plus CH2 double bond CH minus. So this CH2 double bond CH minus, what is the synthetic equivalent for this? The synthetic equivalent for this is simply a acetylene molecule that you have to treat it with the sodamide and get the negative charge. And after, once your job is completed, then you reduce it to that is a partial reduction of triple bond to double bond by using a Lindlar catalyst. So this best synthetic equivalent for CH2 double bond CH minus is the acetylene. So that is the best synthetic equivalent for this. Now look at the synthesis. This one plus acetylene, which is treated with the base acetylide. Now this acetylide attack on the carbonyl group, and this changes to O minus, and after hydrolysis, that is, it abstracts the proton from solvent, it gives OH. Then we have to reduce the triple bond to partial double bond, and again that reduction is a cis reduction, that is a Lindlar catalyst. So triple bond changes to double bond. Next job is you have to go for the heat. That is, the first reaction is heat, and the second reaction is, so due to heating, there is a removal of water molecule, and then it is treated with the quinoline. So Diels-Alder reaction takes place. So due to heating, minus H2O, so minus H2O, and in presence of quinoline, there is a reaction with what? That is a Diels-Alder reaction. So again, you need there a heating. Now this is the new target molecule. Again, whatever the required conditions are there, that is a six-membered ring, and anti to that there is a substituent, and again the substituent there is a electron withdrawing group. So these are the electron withdrawing groups present here. The double bond is there in the six-membered ring, but there is no double bond here. So first of all, we are going to go or do the retro-Diels-Alder reaction for this ring first of all. So go the retro-Diels-Alder reaction with this. So after this, it gives compound, it gives a target molecule, that is, we can consider this is a new target molecule A. So look at, in case of A, that what you need, this plus a butadiene. So look at here A, what we had to do, we want a double bond here. As there is no double bond, then we cannot go with the Diels-Alder reaction. So we need a double bond. So here, what we had to do, you go for the FGI here, write down FGI and place the double bond there. So place the double bond here. Now you can go again a retro-Diels-Alder reaction. So mention on the arrow retro-Diels-Alder reaction. Again you do one more Diels-Alder reaction. So again it gives a furan plus a substituted. Now look at the synthesis. So the compound B. So this we already discussed in previous example. So that we had to do the reaction of these two and synthesize the B. Once you get the B, then this double bond, we had to reduce it by the H2 palladium. That reduces the more accessible non-conjugated double bond. So this double bond is non-conjugated double bond. So this double bond is reduced. So after reduction of this double bond, it gives this compound, and again it is treated with one more butadiene molecule, and again one more Diels-Alder reaction, and that gives the target molecule. So look at the stereochemistry of this group. that the stereochemistry of this two group is alpha. So why the stereochemistry of this two group is alpha? The reason behind is one more ring is going to form from this side. So automatically this stereochemistry cease again, because in a six-membered ring, we cannot have a trans double bond. So whatever the stereochemistry of this two group in the reactant molecule, it maintains that stereochemistry in the final product. This is the again one more target molecule. Now, as we discussed in previous example, a double bond is there. So whatever the requirement is there, that is fulfilled over here. A double bond is there. Anti to that there is a substituent. But the thing is what this carbon is not a electron withdrawing group. So for that, we have to convert both these groups into an electron withdrawing group, as both are the identical branches, CH2OH, CH2A. So we have to convert both of them into a different functional group, that is the ester functional group. So first your duty is to convert CH2OH group. So this CH2OH group, we have to convert it into a ester group, so that now here our requirement is fulfilled here, that is we have a electron withdrawing group. Then we go with the retro-Diels-Alder reaction. So due to Diels-Alder reaction, it gives this. Now look at the stereochemistry of this two ester group. It's a trans stereochemistry. So look at this double bond. Again, you can see it is a diethyl fumarate, a trans geometry across the double bond. The synthesis is simple. Substituted betadine plus diethyl fumarate. It gives Diels-Alder product. So this is a Diels-Alder reaction. You write down on arrow, heating pi 4s plus pi 2s. That you write down by your. Now, next is what? You don't want COET group. Instead of that, you want a CH2OH group. So ester group is reduced by lithium aluminum hydride, and it gives the target molecule. So the target molecule is obtained after the reduction with lithium aluminum hydride. Now this is the new target molecule, and you can see so many rings are there. But among that, look at the central ring. In the central ring, the requirement fulfilled by these two groups, that is electron withdrawing groups, are there. And again, one more double bond is there, which is exactly anti with the substituent. But as it is a aromatic ring, therefore our first duty is to, what we had to do? We had to do the FGI for this. So first our duty is to remove the double bond and go with the FGI. So remove these double bonds and go as do the FGI. So that is your, that is aromatic nature we have to remove first of all. So after FGI, what you do? You remove this double bond. So double bond, this we have to remove. So only this forms a double bond here, it forms a double bond here. So it gives this plus what? Plus double bond COCH3. So this is COCH3. Again, look at the stereochemistry. It is on the same side. So naturally it is what? It is a dimethyl malate. So it is dimethyl malate. The stereochemistry is cis. Now next retro is, look at next retro, PH, CH, double bond, CH, double bond, CH. So double bond is there. So among that double bond, whenever a double bond is there, we always ask the question to that double bond, is it inside the cycle, or it is not a part of a cycle? So now it is not a part of a cycle, so we can go with the retro-Wittig reaction. So retro-Wittig reaction, what we have to do in retro-Wittig reaction, which double bond we have to consider, whether this double bond we have to consider or this double bond we have to consider, that's the question. Now look at here, as we consider this double bond, then due to consideration of this double bond, this is a known compound, that is cinnamaldehyde. So indicating what? That this carbon having a carbonyl group and this carbon having a Wittig reagent, that is Br here. So CH2Br. So here that is the, this one is the Wittig reagent, and another one is, this is the known molecule cinnamaldehyde. So which it's not needed to go the retro of this. Now the synthesis. In the synthesis part, so this is what? This is a paracresol, which is treated with the first of all base. So base abstract this proton. So proton is abstracted, and then there is a generation of negative charge here, and then it attack on the dimethyl sulfate, and the methylation is here. So the second step is what? There is a bromination takes place on methyl group, and that is a bromination in presence of photons, that is a photolytic reaction. It gives CH2Br. Now that we have to convert it into a Wittig reagent, so that we have to treat it first of all triphenyl phosphine. The second compound is base, that is N-butyl lithium. The solvent used for this reaction is THF, and then you have to do the Wittig reaction. So here is the Wittig reaction. So that we have to treat it, here you have to treat it with the cinnamaldehyde. So once you do this, it gives this compound plus this one. So this, now this is again a heating. This one is a Diels-Alder reaction. Write down on arrow Diels-Alder reaction. So complete the mechanism here. So after this, it gives this compound. So here that is that FGI. Now we had to convert first of all. Look at the synthesis. So due to FGI, instead of aromatic ring, what we had to do? We had to do it in a cyclohexadiene. That is this FGI, that structure you have to write here. So here this structure you have to write, that convert it into a cyclohexadiene, and then you go the retro Diels-Alder reaction. So then you go with the retro Diels-Alder reaction. So after that, now it's just by using a simple air oxidation, this is converted to aromatic compound readily, and it gives the target molecule. Now the condition is here that a double bond is there, but anti to this there is no electron withdrawing group. So first our duty is to get the electron withdrawing group here. So first of all, we have to consider this is a alpha beta unsaturated carbonyl compound. So the first duty is to consider alpha beta unsaturated carbonyl compound. So because of that, you disconnect this bond, and now it gives at beta carbon, always you place the carbonyl group. So the requirement is fulfilled over here, and this part is now, the remaining part is CH2 minus COH, and CH2 minus COH, the best synthetic equivalent for this is, it need the control, that is diethyl malonate. So that is the best synthetic equivalent for this synthone, diethyl malonate. Now next one is, this is a retro Diels-Alder reaction. So do the Diels-Alder reaction, and after this it gives this plus double bond CHO. So do the correction here, double bond CHO, that is dienophile. So this is what? Vinyl aldehyde that can be obtained by retro Manich reaction or retro aldol reaction. Now look at this. So what we have done over here, that is a FGI, functional group interconversion. So instead of double bond, we have added a water molecule here. So that is a retro dehydration reaction. So retro dehydration reaction, again add H and OH. So OH, that has to be added to the most hindered carbon. So OH here, and here is the OH. Next, this is nothing but a very simple Pinacol reduction reaction. So this is a retropinacol reduction reaction that is done by the mercury amalgam, that is magnesium amalgam in presence of benzene. So two molecules of this acetone, it gives a diol. So look at the synthesis. Acetone, it is treated with the magnesium amalgam in presence of benzene. It gives the diol. Then go for the dehydration reaction by using alumina. So in presence of alumina, water molecule removed and it gives you a diene, substituted diene. Then you have to treat it with the vinyl aldehyde. So after this, it gives the Diels-Alder reaction. So right on arrow, heating. So this is the adduct. After this, that you have to treat it with the diethyl. This is simply malonic acid. You can also take diethyl malonate, that doesn't matter. So that you have to treat in presence of basic condition. So it attacks, so base abstract this acidic proton and then it attack on the carbonyl group of this. So base abstract this proton so that it attacks here and complete the mechanism of this, and then two acid groups are there. You remove one of the acid group by decarboxylation, and at the same time the water molecule also get removed and it gives this double bond here.